Did you know that each year the world builds structures so massive, skyscrapers scraping the sky, bridges spanning vast canyons, ships larger than city blocks, that they require metal parts shaped with forces equivalent to thousands of tons and precision measured in mere millimeters? This isn't just cutting and welding metal in a workshop. This is bending steel plates thicker than your arm, forging colossal parts under unimaginable pressure, and machining giant structures with surgical accuracy. Get ready to witness the most impressive, largest-scale metal fabrication methods on Earth, uncovering the hidden power and precision that builds our modern world. The sheer scale of metal fabrication hits you right away on the factory floor. We're talking about moving and shaping pieces that weigh tons. One of the most fundamental and visually impressive processes is metal bending. Forget bending a paperclip. Imagine bending steel beams strong enough to support a building, or curving thick metal plates for ships and pressure vessels. Massive machines called press brakes or roll benders use incredible hydraulic force to shape metal. Picture a giant press pushing down with thousands of tons of pressure to put a precise bend in a steel beam, or colossal rollers curving a thick steel plate into a perfect cylinder. These aren't just big tools. They're feats of engineering designed to apply immense force with fine control. On the biggest scale, you see specialized machines like the FKB 3-roll plate bending machine, capable of shaping massive steel plates for tanks, wind turbines, or ship hulls with incredible accuracy. Software like Bentronic controls the rollers with millimeter precision, even on pieces the size of a room. Another impressive example is bending giant steel beams for structures. Machines like the Faction R CMI use powerful hydraulic rolls and guide systems to curve huge I-beams or H-beams into exact shapes needed for complex architecture or bridges. Applying that much force while maintaining the beam's structural integrity is a true industrial art form, making metal flow like clay, but under thousands of tons of pressure. Another mind-blowing method is metal forging. This is using localized compressive forces, often with immense power and heat, to shape metal. Think of a blacksmith, but on a scale where the hammer is a machine delivering thousands of tons of force. In massive forging presses, heated metal billets, solid blocks of steel, are pounded or squeezed into complex shapes. This process changes the metal's grain structure, making the finished part incredibly strong and durable. This is how critical components for aircraft landing gear, engine parts, or even massive artillery barrels are made. At places like the Wortel at Arsenal, you see iconic machines like the rotary forge. This is a different kind of forging, using rotating dies to hammer and shape a heated steel billet into a hollow tube, like a cannon barrel, with incredible speed and precision. These machines have been operating for decades, playing a vital role in producing thousands of heavy-duty barrels for military systems. The sheer force and rhythmic pounding of these colossal machines working on red-hot metal is one of the most dramatic spectacles in metal fabrication, showcasing raw power precisely controlled. Once metal parts are formed by bending or forging, they often need precision finishing. This is where machining comes in, using tools to cut away material and achieve exact dimensions and shapes. On the biggest scale, this involves massive CNC, computer numerical control, machining centers working on parts that weigh many tons. Imagine a machine tool the size of a small house, precisely cutting, drilling, or milling a giant metal casting or forging with micron-level accuracy. Sophisticated software controls these machines, making complex cuts and achieving tolerances required for critical components in aerospace, heavy machinery, or energy production. Precision machining isn't just about size, it's about achieving incredible accuracy on massive objects. Machines use advanced cutting tools made of hardened materials, sometimes cooled with high-pressure coolant, to cut through tough alloys. On critical components like gearbox housings, turbine shafts, or large crane parts, surfaces must be machined to tolerances that ensure perfect fit and smooth operation under immense loads for decades. It's a process where technology allows engineers to sculpt giants with the precision of a jeweler. Beyond these core methods, metal fabrication involves a host of other impressive processes on industrial lines. Cutting is a crucial first step, using powerful lasers, plasma torches, or water jets to slice through thick metal plates with incredible speed and clean edges. Welding is joining metal pieces together, from automated robotic welding arms building vehicle frames or ship sections, to skilled human welders performing critical structural welds that must withstand massive forces. Surface treatment like sandblasting and industrial painting or coating lines protect the metal from corrosion and give it its final look. Throughout all these stages, from the arrival of raw metal plates and beams to the final finished and assembled components, rigorous quality control is paramount. Industrial scanners, ultrasonic testing, X-rays, and precise measurement systems check every weld, every dimension, every material property. Experienced technicians and engineers oversee automated inspection systems and perform manual checks on critical points. A blend of high-tech monitoring and human expertise, ensuring that these massive metal parts meet the highest standards of strength, precision, and safety required to build skyscrapers, planes, and infrastructure. These massive metal fabrication facilities are not just factories. They are cathedrals of engineering power and precision. They process hundreds of thousands of tons of metal each year, shaping it into the backbone of our cities, transportation, and industries. It's a testament to human ingenuity and technological advancement, taking raw materials and applying immense force and incredible accuracy to build the physical world around us. It's a hidden, necessary industry that few people ever see. So, the next time you look up at a skyscraper, cross a bridge, or see a large machine at work, remember the mind-blowing industrial process that created its metal bones. The bending of giant beams, the forging of colossal parts, the precision machining of massive structures. It's all part of the amazing world of metal fabrication. It's a fascinating look into the power and precision that builds our modern world. What part of these impressive metalworking methods surprised you the most? Let us know in the comments. Did you know that each year the world faces the challenge of decommissioning millions of old electrical transformers? These metal giants, often found quietly powering our neighborhoods, can hide an incredibly dangerous secret. Many older units are filled with highly toxic chemicals, like deadly PCBs. A single misplaced cut or accidental spill could cause severe, long-lasting environmental damage across vast areas. Taking down these hazardous units isn't a typical scrapyard job. It requires a specialized, highly precise, and incredibly dangerous industrial process happening behind closed doors. Get ready to see the intense operation to safely dismantle these toxic time bombs. So, why exactly are these old transformers so dangerous? For decades, many relied on a coolant liquid called ascarel, which contains polychlorinated biphenyls, or PCBs. These chemicals are terrifyingly persistent in the environment. They don't break down easily, and they are highly toxic to humans and wildlife. Even a small leak from a neglected unit can contaminate soil and water for generations. Modern transformers use safer, non-toxic oils, but the legacy of PCBs in older units means they cannot simply be scrapped like regular metal waste. They demand specialized, heavily regulated facilities designed specifically to handle these hazardous materials with extreme care and containment. The intense process begins when old transformers, often behemoths weighing thousands or even tens of thousands of pounds, arrive at these specialized decommissioning plants. Picture massive yards filled with these silent, potentially hazardous giants, waiting to be processed on a dedicated industrial line. The absolute first step isn't dismantling or cutting. It's meticulous documentation and assessment. Each arriving unit is rigorously inspected, its history and potential contents checked to determine if it likely contains PCBs or other hazardous materials. They are categorized based on size, type, and estimated contamination level. This initial sorting on an industrial scale requires heavy-duty lifting equipment, massive cranes and powerful forklifts, just to move these incredibly heavy pieces of electrical history into position for the next stage. Once identified, categorized, and positioned, the transformers move onto the dedicated high-containment processing lines. The absolute priority here is total containment and zero exposure. Every single step is designed with redundant layers of safety to prevent any spills or contact with the toxic materials inside. Workers operating on these lines are encased head to toe in specialized protective gear. Full chemical suits, filtered respirators, multi-layered gloves. The air quality within the facility is under constant real-time monitoring. These are not standard factory conditions. They are hazardous material handling zones requiring maximum vigilance. The first critical task on this line is to meticulously drain the internal coolant oil. This oil, especially if it contains PCBs, is the most dangerous component. The liquid heart of the toxic secret. Draining the hazardous oil is a highly precise, high-containment operation, executed with surgical care. Transformers are carefully positioned over multi-layered sealed collection systems, often including large secondary containment basins designed to catch any potential leaks or spills, no matter how small. Workers use specialized pumps, leak-proof fittings, and designated tools to access drain valves and carefully remove every single drop of the hazardous oil directly into secure, heavy-duty, properly labeled tanks. This cannot be rushed. It's a slow, deliberate process. Think of it like disarming a complex device. Every connection, every hose is checked and rechecked multiple times. This step is the most crucial for protecting the environment from widespread contamination and ensuring the immediate safety of the workers directly interacting with the highly toxic liquid hidden within the steel shell. After every drop of oil is confirmed, safely drained, and contained, the transformer must be absolutely de-energized and rigorously verified as safe from any residual electrical voltage. Even units that have been disconnected for years can potentially hold a dangerous charge. Highly trained technicians follow strict, multi-step lockout, tagout, and grounding procedures, physically isolating the unit and discharging any potential buildup to ensure no electrical hazard remains before any physical dismantling tools come anywhere near the unit. Safety protocols here are layered and redundant, because any mistake made at this stage carries the risk of severe injury or worse. With all immediate electrical and chemical hazards neutralized, the physical dismantling begins. The process of breaking down the thick steel shell to access the valuable materials and internal components. This is heavy-duty, industrial demolition work requiring powerful tools. Workers use intense plasma cutters that slice through thick steel casings with incredible heat, powerful hydraulic shears that crunch through metal like paper, and heavy-duty saws. The internal components, massive, heavy copper windings, dense steel cores, and various insulation materials, are often incredibly weighty and must be carefully lifted out section by section using overhead cranes and specialized rigging. Imagine cutting open a giant, multi-layered steel safe filled with tangled, incredibly dense, and heavy metal structures. It's a loud, sparks-flying process, but it's executed with engineering precision to efficiently separate the different material streams. As the transformer is broken down piece by piece on the dismantling line, the various resulting materials are carefully sorted and separated onto different processing conveyors and areas. Valuable metals like the pure copper windings are isolated into their own stream and sent for high-grade recycling. Steel casings, cores, and other structural steel components are separated for scrap metal recycling. Aluminum parts are directed to their specific recycling stream. But the key challenge, the hazardous legacy, lies with the contaminated materials. Any solid components that came into direct contact with the toxic PCB oil, internal insulation paper, wooden bracing blocks, contaminated gaskets, even metal parts that absorb the chemical are now classified as hazardous waste themselves. Handling and disposing of this hazardous solid waste requires extreme care and strict protocols. The safely drained PCB oil, the contaminated solid materials, and even the specialized protective gear worn by workers after handling these substances must be meticulously contained, documented, and transported for disposal according to stringent environmental regulations. This often involves complex logistics chains, moving the waste to highly specialized hazardous waste landfills designed to permanently isolate the toxins, or to permitted high-temperature incinerators, specifically designed and certified to safely destroy PCBs at extreme temperatures. It's a costly, complex, and highly regulated part of the process, a hidden necessary step ensuring those dangerous chemicals never re-enter the environment to cause harm. Despite the inherent dangers and complexities, dismantling old transformers represents a vital dual purpose. Primarily, it's about environmental protection and safely eliminating hazardous waste legacy units. But it's also a significant part of the circular economy and resource recovery. Valuable metals like pure copper, steel, and aluminum, weighing thousands of pounds in a single large unit, are recovered and reintroduced into the manufacturing supply chain. This reduces the need for environmentally impactful new mining operations. So, while the drive is safely neutralizing a threat, the process simultaneously recovers significant valuable resources, making it an essential, albeit dangerous, link in the critical lifecycle management of electrical infrastructure. These highly specialized decommissioning facilities are engineering marvels in their own right. They process hundreds, sometimes thousands of transformers each year, ranging from common small pole-mounted units you see everywhere to massive multi-ton substation giants. Each unit processed represents a potential environmental disaster safely averted and a source of valuable industrial materials recovered, all thanks to incredibly precise engineering processes, cutting-edge safety protocols, and the unwavering skill and courage of workers operating daily in a high-risk, high-containment environment. It's a critical industry that literally cleans up dangerous industrial history. So, the next time you see a transformer quietly working, or simply flip a light switch, take a moment to remember the unseen, dangerous, but absolutely essential industrial process happening far from view. The vital work of dismantling old, toxic giants, protecting our environment and communities from hidden chemical threats, and recovering valuable resources for the future. It's a fascinating, high-stakes look into a necessary industry few people ever see. What part of this hazardous but critical process surprised you the most? Let us know in the comments. It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to negative 260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float-level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create 3 separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. And 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about -260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Imagine this: red-hot metal up to 33 feet long, bending as easily as if it were a sheet of paper. Every year, factories all over the world create millions of parts, from car bodies to giant pipes, thanks to bending machines. But how are perfect bends, channels, and even spiral shapes for oil and gas giants born from cold, formless steel? And how can it be done without wasting tons of energy? Let's dive into a world where metal obeys human will. A bending machine. Think of it like a big construction set for metal. Imagine a flat sheet that needs to be bent into a specific shape. The machine takes this sheet and bends it using special tools to get the desired angle or form. First things first, the metal sheet needs to be checked to make sure it's suitable for the required part. This includes checking dimensions and looking for defects like cracks or breaks. The metal sheet is cleaned of dirt and rust using a wire brush or sandpaper. This is necessary to ensure clear marking and subsequent processing. Markings are applied to the sheet using special tools like rulers, squares, and scribers. The layout includes drawing center lines and contour lines, as well as marking the centers for any future holes in the part. To make sure the markings are clear and don't rub off during processing, the metal surface is coated with a special paint. Dry chalk, a chalk solution with glue, or a copper sulfate solution might be used. After applying the markings, they are checked against the part drawing. In large industrial settings, automated systems are often used to lift and place metal sheets onto the machine. These systems might include conveyor lines and robotic arms that precisely position the metal sheet on the machine's bottom die. In smaller workshops, or during small batch production, metal sheets might be placed manually by workers. Workers in protective suits and gloves lift the sheets using special tools or lifting equipment and place them onto the machine. Metal sheets can vary greatly in size, from small ones easily lifted by hand to enormous ones requiring special lifting equipment. In large industrial settings, you might see sheets up to 33 feet long and up to 10 feet wide. Then, the necessary tools are selected: a punch for the upper part and a die for the lower part. These determine exactly how the metal will bend. During the sheet metal bending process, the machine presses the punch onto the sheet and it bends into the die, forming the required shape. This process allows for creating various shapes and angles, depending on the type of punch and die used. The most common method is V-bending, which is used to create angles of various degrees. This shape is widely used in manufacturing elements for construction, machine, and equipment housings, frames, and so forth. U-bending is used to create U-shaped channels from steel and other metals. This shape is ideal for manufacturing metal profiles and channels. Radius bending is used to make parts with cylindrical or conical configurations. Such shapes are used in the production of pipes, cylinders, and other three-dimensional structures. One variation of polygonal bending used to obtain complex shapes is P-bending. Bending sheet metal allows for creating various shapes and angles, but creating a spiral shape is a more complex process. Spiral forms are usually made using special methods and equipment, such as roll-forming machines. These machines are used to produce cylindrical, conical, and other curved surfaces. They allow for creating spiral shapes by sequentially passing the metal through rollers that gradually form the desired shape. Such machines are widely used in the production of pipes, cylinders, and other metal structures that require a spiral form. While roll-forming machines are operating, you can see how metal sheets pass through the rollers, gradually acquiring the desired spiral shape. Spiral forms are used in various industries and everyday applications. They offer high strength, excellent conductivity, resistance to corrosion, and fatigue. Springs, connectors, heat exchangers, electrical engineering and electronics, the oil and gas industry, chemical processing, and medical instruments all use products with spiral shapes. For example, in beryllium copper spiral tubing, the spiral form is used in 50% of applications due to its high conductivity and strength. Spiral cables are used in over 70% of industrial automation systems because of their flexibility and resistance to mechanical wear. Spiral springs are found in over 30% of mechanical drives due to their ability to provide varying spring forces. Spiral pipes, often referred to as coiled tubing, offer several advantages in the oil and gas industry. They can easily adapt to changes in elevation and direction during the transport of oil and gas. This is particularly important when constructing pipelines in complex geological conditions. Coiled tubing has a spiral seam, which facilitates installation. This can reduce assembly time compared to traditional pipes with straight seams. Coiled tubing is used in well clean-out technology after hydraulic fracturing. Nitrogen is pumped through these tubes to wash out proppant from fractures, which increases maintenance intervals and reduces the time needed to bring the well back into operation. Metal forms can be made from various materials, such as steel, aluminum, or copper. The choice of material depends on the requirements for the product and the possibility of reuse or recycling. Traditional manufacturing methods can involve high energy and resource consumption, which can negatively impact the environment. However, modern technologies, like using renewable energy sources and optimizing production processes, can significantly reduce this impact. Metal forms can be recycled and reused, which reduces waste and the need for virgin materials. This is especially important for steel and aluminum products. To protect metal structures from corrosion, powder coatings are often used. These are more environmentally friendly compared to traditional paints because they do not contain organic solvents or harmful substances. Switching to solar, wind, or hydropower can reduce greenhouse gas emissions by 70 or even 90% compared to traditional energy sources. Improving technological processes and automation can reduce energy consumption by 20 or 30% and cut waste by 25%. Reusing metal forms reduces waste by 50 or even 70%. Every single year, more than 200,000 hydrocycles are sold all around the globe. And the overall market for this type of equipment exceeds $2.5 billion United States of America dollars. But how does a piece of composite material turn into a genuine water monster that can accelerate up to 70 miles per hour? What makes the Japanese Yamaha factory the largest hydrocycle manufacturer in the entire world? From automated hull molding to the most advanced engines and on-water testing, today we are going to unveil every secret of their production. Fasten your seatbelts because we are heading into a realm of high speeds and groundbreaking innovations. The design of hydrocycles begins with conceptual ideas and essential requirements for technical specifications. The very first stage involves identifying the target audience and the purpose of the hydrocycle. It can be a recreational model, a sports or extreme hydrocycle, or even specialized versions for fishing or rescue operations. Designers and engineers must consider not only the visual appeal, but also factors such as maneuverability, stability, top speed, comfort, and water safety. They carefully think through each detail so that the final product meets the needs of both beginners and seasoned riders. According to Statista, the global hydrocycle market by the year 2027 will grow to over $2.5 billion United States of America dollars, with an annual growth rate of 8.3%. This impressive forecast shows just how much interest hydrocycles continue to generate in different parts of the world, especially as new technology makes them more efficient, eco-friendly, and fun to ride. One of the biggest markets for hydrocycles is the United States of America, where more than half of all hydrocycles worldwide are sold. This country remains a leader in water sports development, partly because of its numerous resorts, lakes, rivers, and coastlines, which make hydrocycles immensely popular among both local residents and tourists. Hydrocycles are also well liked in Australia and Japan, where water activities are an integral part of cultural traditions, and people love to explore different forms of aquatic adventure. During the development stage, important factors include the design of the hull, which must be light yet strong and resistant to mechanical damage. For this purpose, high-quality materials such as fiberglass, composites, and aluminum are used to achieve the required rigidity without adding too much weight to the hydrocycle. Another critical consideration is the choice of engine. Most hydrocycles use internal combustion engines, although a growing number of manufacturers are experimenting with electric models, which offer cleaner emissions and produce less noise. In modern hydrocycle design, special attention is paid to innovative technologies, including digital control systems, integration of the global positioning system, and sensors for monitoring the condition of the equipment and improving navigation. These features not only make the experience more convenient for the rider, but they also boost overall safety through automatic stability control systems or engine rotation alerts. All of this simplifies the hydrocycle piloting process and makes it safer, even for first-time enthusiasts. The United States of America holds over 50% of the global hydrocycle market. Another notable trend is the rising demand for electric hydrocycles. Although they currently occupy only a small share of the market, their environmental advantages could make them a key part of the hydrocycle industry's future, since they help reduce emissions and lower noise pollution levels on the water. An essential element of design involves creating an ergonomic layout that ensures comfort during lengthy rides or races. Seats must be comfortable and provide proper support for the rider's posture, while also featuring a non-slip surface that holds up in wet conditions. Additionally, hydrocycles are equipped with various features, such as extra storage compartments, waterproof pouches, and cooling systems that help the vehicle operate at high revolutions over long periods. Developing new models also requires numerous water tests to check how the hydrocycle performs in real conditions. This process helps identify any weaknesses in the design or technical parameters, which are then corrected before the start of mass production, guaranteeing that customers receive a high-quality product. The hydrocycle development process is extremely detailed and demands meticulous attention at every phase, from designing the hull to testing the final product. Engineers, designers, and manufacturing specialists must work in close collaboration to produce equipment that is not just powerful and fast, but also safe and comfortable for users. Hydrocycles need to be easy to maneuver on the water, while also having enough durability to withstand heavy loads, water pressure, salt, ultraviolet radiation, and other environmental factors. These stringent requirements mean that the choice of materials for different hydrocycle components must be carefully evaluated to balance weight, strength, and resistance to corrosive elements. First and foremost, a key element of any hydrocycle's construction is its hull. This is one of the main parts that must be strong enough to resist mechanical damage and, at the same time, provide optimal hydrodynamic characteristics. The most common materials for hull manufacturing include fiberglass, composite substances, and aluminum. Fiberglass is selected because it offers high strength at a low weight and is resistant to corrosion, making it ideal for use in aquatic environments. In addition, it can be molded easily, allowing engineers to create sleek, aerodynamic shapes for the hydrocycle hull. Composite materials, which include polymers reinforced with fibers such as carbon or Kevlar, are even more advanced, delivering greater strength while reducing weight. They also exhibit excellent resistance to ultraviolet exposure and chemical agents like salty water solutions. By combining these materials, manufacturers can cut down on hydrocycle weight while improving speed and maneuverability, which is especially beneficial for sports-oriented models. When it comes to internal components, such as fuel tanks and cooling systems, manufacturers often rely on stainless steel or specialized plastic blends. Stainless steel is a long-lasting material that resists corrosion, making it perfect for repeated contact with water and various liquids. Plastic blends, such as high-density polyethylene, are used due to their lightness, durability against chemical and mechanical impact, and ability to function effectively for extended periods in high humidity conditions. Another crucial consideration is the choice of materials for hydrocycle engines. Lightweight yet powerful substances are essential for achieving high revolutions without sacrificing endurance. Typically, engine components are made from metal alloys, including aluminum, titanium alloys, or magnesium. These materials have low density, which helps reduce engine weight, and they have excellent thermal conductivity, which is critical for efficient cooling and overall engine performance. One well-known hydrocycle manufacturing facility is located in Japan, operated by Yamaha Motor Company, which is widely recognized as one of the leading brands in the watercraft market. Situated in the city of Iwata in Shizuoka Prefecture, this factory produces not only hydrocycles, but also other types of water transport and their engines. The Yamaha Motor Factory spans approximately 250 acres, making it one of the largest facilities in the world dedicated to water equipment production, including hydrocycles. The site specializes in manufacturing a broad range of water transport products, including diverse hydrocycle models, boats, yachts, and other motorized water vehicles. Every year, this factory turns out thousands of products, including over 60,000 hydrocycles annually, which secures Yamaha a substantial market share in the water transport sector. Thanks to the factory's expansive premises, every stage of production, from assembly to testing and packaging, can be carried out efficiently and in one location. One of the main automated lines is responsible for forming hydrocycle hulls using materials such as fiberglass and composites. This line is equipped with robotic arms that precisely shape and join individual hull components, delivering the exact design contours and a smooth exterior finish. In addition, automated welding and painting systems are used to process metal parts, such as engines and their subsystems. The line features robotic welding machines that provide accurate, high-quality welds, as well as automated painting systems that evenly coat components and offer reliable protection against corrosion. This advanced technology helps ensure the product maintains a pristine appearance and robust structure over an extended service life. The assembly lines have a real-time quality control system, which automatically identifies defects at any stage of production. This includes visual inspections using cameras and scanners capable of detecting even the smallest flaws in parts, allowing the factory to preserve the highest possible product quality. A distinctive feature of this factory is its extensive automation in the packaging and shipping phases. Once Hydrocycles have passed all quality checks, they move on to automated packaging lines, where robotized systems assemble boxes and secure the Hydrocycles inside transport containers. This process enhances shipping safety and streamlines logistics, ensuring that the products are delivered to customers in excellent condition and on schedule. The Yamaha factory continuously adopts the latest technologies in water equipment production. For instance, they use three-dimensional printing to create prototypes of new models, enabling faster testing and refinement of their designs. Moreover, the facility employs pioneering materials that help reduce the weight of Hydrocycles, increase their corrosion resistance, and extend their service life. They also make active use of intelligent production management systems, which optimize manufacturing processes, cut down on costs, and shorten the time needed to produce each unit. As a result, the factory can expedite Hydrocycle manufacturing and boost output volume, illustrating Yamaha's commitment to continuous innovation and leadership in the fast-paced world of Hydrocycle development. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination — gasoline still contained lead back then — and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, They are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula One race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative plaid carbon-wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual motor versions. Tesla pushed forward and introduced its plaid carbon-wrapped motor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid carbon-wrapped motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100th seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary plaid carbon-wrapped motor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry.